Hi, I'm Qizhen from Hong Kong University of Science and Technology. Today with my co-author Luping, we are honored to present Metis, a learning-based scheduler tailored for clusters hosting long-running applications, or LRA for short. LRAs are typical workloads in production clusters. They are also known as latency-critical services like streaming processing, interactive data analytics, caching service, and etc. Unlike batch jobs that run in ephemeral task executors, LRAs run in long-lived containers with durations spanning hours to months to serve queries. Therefore, they usually occupy a large amount of resources. In Alibaba's cluster, LRA runs on 94% CPU core and 37% memory resources. Similarly, Microsoft assigned a substantial portion of machines or even dedicated clusters to LRAs. And Google cluster shows similar phenomenon that production jobs are more likely to run for a long time. However, it is non-trivial to schedule LRAs, not only due to their stringent SLO requirements, but also of the sophisticated performance interactions among them. More specifically, LRAs commonly have I/O dependencies in that one's input depends on another's output, in which case these instances are preferred to be co-located on the same machine to reduce data transmission. We term such property as affinity. For example, in our benchmark, we deploy two deep learning inference workloads, the image super resolution and mixednet model server. They host a long-running services to process the images input from another caching service, Metis. Obviously, a co-located Metis instance will speed up the data fetching process and reduce the response latency of two services. This affinity relationship is represented as the green arrow in the figure. In contrast, some instances will contain shared resources, such as CPU last level cache, memory bandwidth, network I/O, and etc. It is quite common to observe such phenomenon of more or less intensity among co-located workloads, and it is better to scatter these workloads among different machines. To illustrate this point, we also include Yahoo Cloud Serving benchmark workloads, file checksum services, and video scene detection service in our benchmark. The red arrow in the figure shows the anti-affinity relationship among them. To tackle these challenges, we propose Metis, a learning-based LRA scheduler. It takes LRA launching requests and group schedules these containers to cluster nodes for better performance. It has three highlights. Firstly, it always pursues the best end-to-end performance of whatever metrics, like throughput, latency, resource utilization, or even their combinations. Secondly, it does not require any prior knowledge. Given historical trace data, it can automatically learn to capture their complex interactions. Thirdly, we improve the vanilla learning algorithm and make it scale to thousands of nodes within moderated scheduling latency. In the following parts, we will first show how Metis outperforms prior arts, then show the key scalable algorithm, and finally demonstrate its performance in evaluation. As the state-of-the-art LRA cluster scheduler, Media is deployed in Microsoft and follows the constraint-based workflow. Before the scheduling starts, it first requires scheduler operators to identify complex container interactions based on their experience and summarize them into placement rules. Then in the scheduler, they should manually encode these rules as container placement constraints, like port affinity and anti-affinity. With these constraints, Media formulates them as ILP problems to minimize constraints violation and other targets, and call the solver to work out a placement solution. As the last step, it schedules its constraints according to the solution to the nodes. We find that it has several problems. The constraints summarized by the expert requires onerous human efforts, yet can still be inaccurate. Also, it does not scale, given the emergent new applications every day. And solving the ILP is very slow. It takes over 10 hours, according to experiment, to place 3 sovereign containers on a 700 machine cluster. More importantly, this approach still cannot guarantee optimal performance. Since the placement constraints only provide a qualitative scheduling guideline, but do not quantify the actual performance impact. For example, to what degree can the throughput be harmed if violating a certain constraint? This situation becomes worse in face of conflicting constraints, where media may mistakenly choose to violate those constraints with more impact. Recall the MixNet model server and Redis workloads. MixNet can benefit from Redis and significantly improve its throughput, while its extra workload will slightly reduce Redis throughput. This forms a pair of conflicting constraints. An intelligent scheduler should always prefer co-locating MixNet and Redis rather than the other way around, but media does not always do so. Consider a specific scenario shown in the figure, where we have 14 containers of 7 applications to reside on 6 nodes. We profile their performance interactions, summarize constraints, and schedule them with media and Metis, respectively. As a result, media gives the placement shown on the left, with the minimum number of constraints violated in this case by scattering Redis and corresponding deep learning workloads. Our scheduler Metis finds a better placement shown on the right. So it violates more constraints. It evaluates the placement directly by end-to-end performance, avoid the trap of conflicting constraints by co-locating MixNet and image super resolution with Redis, therefore achieves higher average throughput in total. Let's see how Metis works it out. It aggregates containers requests into groups to be scheduled in step 1. Then in step 2, applying reinforcement learning with the cluster environment simulator. It initializes a new learning agent for each group and keeps training it until the agent provides the best placement in the current situation. In steps 3 and 4, Metis collects placement decisions and launching containers accordingly in the cluster. Then in step 5, it runs a profiler to monitor workloads performance and gets their traces. These traces will be fed back to the environment simulator to improve the simulator, which is the step 6, so that it later can make more accurate performance predictions for the RL training. The implementation of all the algorithms, baselines, and benchmark workloads are open sourced on GitHub. One may note that our method differs from the traditional RL approaches in that Metis trains new dedicated RL agent on the spot for each input container group. The idea is to trade computation and latency for better performance. Since we find that training one single agent offline and deploying it to make online decisions for all scenarios usually gives inferior performance. It is because of the highly variant input. The workloads currently running in the cluster will change after each deployment, and the input container group can also have massive combinations, say over 2 million possible outcomes of picking 30 combinations from 7 applications. The offline train general policy can hardly provide optimal solution in all these cases. Instead, a dedicated agent in each scenario is usually better in performance. We have to admit that the online model training requires more resources, gives longer scheduling latency, and raises scalable challenges. In the next part, my co-author Luping will present our design in algorithm to serve these problems.
And next, I will introduce the following several parts. Given the observations above, we propose to employ the modern machine learning techniques to place containers. In specific, we will train the reinforcement learning agents to learn the container placement policies. At a high level, this method could provide the following benefits. First, instead of summarizing and then enforcing the placement constraints, training a reinforcement learning agent typically involves an automatic try and true process, from which the placement behaviors can be learned in an end-to-end manner. To be more specific, the detected intercontainer interactions will not be expressed as mathematical models, such as placement constraints. Instead, this information will be embedded as the neural network parameters, which will be automatically updated by the interaction with the environment. Second, we can train the reinforcement learning agent to optimize the various scheduling objectives without the limitations such as the linear or convex requirements. In fact, we can optimize arbitrary objectives by quantifying it as a metric and feeding it to the reinforcement learning agent as the reward signals. Then, the most important benefit is that this method is scalable in large-scale clusters compared with the aforementioned ILP solutions. Ideally, we can offline train the reinforcement learning models based on which the online scheduling decision can be made through only a neural network forward propagation, whose latency is negligible compared with solving a large-scale ILP problem. As we will show next, this scalability cannot be obtained trivially, and we can design tailored IL framework to reap the scalability benefit. We now show that directly employing the vanilla reinforcement learning techniques, such as the policy gradient or actor critique, cannot perform well when the problem scales. In specific, in production clusters, we will handle thousands of machines, meaning that when we place the containers, the hosting machine candidates involve thousands of choices. When using reinforcement learning to solve this problem, that means the reinforcement learning agent action space is several thousand, and therefore the state space will correspondingly exponentially increase. Training a single neural network will fail in handling such a high variant dynamics. The figure below shows an example when training the reinforcement learning agent to place several hundred containers to a 81 node cluster. We show three different reinforcement learning frameworks of which the core algorithms are all the policy gradient. We plot the training curves regarding the average container RPS. And as we can see in the green dotted line, directly using vanilla policy gradient spends rather longer training time, yet providing poor eventual performance. And we will next show that our tailored design in handling such a scalability issue. At a high level, other than directly employing a single reinforcement learning model to handle such a large-scale problem, we use another RL paradigm, namely hierarchical reinforcement learning, aka HRL. Basically, HRL is designed to decompose the initially complex learning task into multiple layers of simpler subtasks. Each subtask is independently modeled as a single reinforcement learning problem with its own state, action, and reward. Come back to our container placement problems. From top-down view, we manually separate the cluster into several subclusters, each with a smaller size. For example, a cluster can be naturally divided into racks. For each container to be placed, we first select the optimal subcluster to place it, and then we choose the optimal hosting machine within such a subcluster. Now, we divide the original reinforcement learning job into two RL tasks, the high-level task to select a subcluster and the low-level task to select a hosting machine. Each has a smaller scale and hence can be solved more efficiently. Besides, for the low-level tasks, different subclusters can share a single reinforcement learning model. That means Although different subclusters may have different attributes, such as different cluster sizes or different hardware equipments, we can embed these features into cluster states and thus reuse the RL models in all these subproblems. We therefore achieve spatial reuse of the building blocks, which is important in handling the scalability issue. And we next show some evaluation results of our reinforcement learning design. As Qizhen has discussed, we have implemented the entire placement process as a plug-in atop the framework of Docker Swarm and execute some evaluation experiments in Amazon EC2 clusters. In specific, our experiments are running in two clusters, the medium one with 81 nodes and a larger one with over 700 nodes. We implemented 7 real-world long-running applications and assumed that all their Docker containers have the identical resource demands. And our baselines include constraint-based media and learning-based Paragon. We first compare Metis and the two baselines in terms of the scheduling performance in the medium-size cluster. The figure on the left plots the eventual container RPS under these schedulers. We can clearly find that Metis continuously outperforms the baselines by outputting higher average container RPS. And to quantify this benefit, Metis achieves up to 25% and 61% higher RPS, respectively. On the other hand, the figure on the right compares the decision-making latency. As we can see, owing to the simple greedy algorithm, Paragon has the shortest latency in a few seconds, and Metis, thanks to its highly optimized design, can find the optimal placement in less than 10 minutes. On the other hand, the longest latency is measured in media, as it needs to solve a complex ILP problem involving over 100,000 constraints. And we next emphasize the scalability of Metis by stress testing it in scheduling several thousand containers in a large cluster. Metis can still make timely scheduling decisions within 1 hour. And on the other hand, we found that our HIL design accelerates the training at the cost of lower decision performance. And the figure below quantifies these impacts. As we can see, the HIL design dramatically accelerates the reinforcement learning convergence by up to 95 times with less than 10% loss of RPS values. Finally, we show that Metis is a general-purpose scheduler that can be used to optimize various objectives beyond RPS. The figure above compares the schedulers in maximizing the container RPS SLO. Here, instead of the average container RPS, we consider the percentage of containers of which the RPS is higher than a predefined threshold, aka SLO satisfaction. Similarly, we see the continuous outperformance of Metis. The figure below shows that Metis can simultaneously achieve multiple objectives by aggregating them into the reward signal using summed weighted. By doing so, we see that Metis can smoothly strike the balance between higher container RPS and lower cluster resource fragmentations. And above are our presentation results. All the questions are welcome. Thank you.